Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Sofia Sheikh with us today. Hello, Sophia.
Hello, thank you for having me.
Well, thank you so much for agreeing to talk about your very awesome article, which we'll get to here shortly. Let's see, where shall we start? And Sophia, what is your geolocation? Where are you at?
I am in San Francisco, California.
Okay.
Uh, I work at the SETI Institute now, and so that's in Mountain View, and I have a long commute, but I love San Francisco, so, worth it.
City. Let's see, and it is March 19th of 2025 as we record this. Is spring starting to make an appearance in San Francisco, the Bay Area?
Well, we kind of say that San Francisco has like three or four false springs before true spring, and so we're exiting one of the false springs at the moment.
One of those springs happens in the summer, of course, you know. So
Absolutely.
it's all very good. Very cool. Very nice. And Sophia, what do you like to do for research?
My primary bread and butter research is radio technosignature searches with the Allen Telescope Array,
Cool.
but I also do a variety of other observational radio astronomy topics like pulsars, fast radio bursts, RFI mitigation, these sorts of things.
Very nice. And speaking of, you have some pretty awesome pictures over your right shoulder, I think it is, if I got the parity right. What are those?
These are some pictures drawn by my partner's brother.
Very good. Very good. They look technically accurate. They're really cool. Very cool. All right. And that is going to bring us to this very awesome, oops, article. This is an AJ, Earth, detecting Earth. At what distance could Earth's constellation of technosignatures be detected with present-day technology? And Sophia, take us away.
Thank you so much. I'm really excited to talk about this article because it's one of the most fun papers that I have worked on in my career, and also one of the most uh, interdisciplinary as
Mhm.
far as astronomy subfields go. So I have to shout out my co-authors here all just contributed so significantly to this work
Cool.
um, across wavelengths, across disciplines. Many wonderful people I got to collaborate with as part of the Characterizing Atmospheric Technosignatures group led by Adam Frank.
Very good. Cool. Good shout out. Okay, let's go.
So, yeah, I guess starting with the introduction here, uh, we kind of dived into this introduction thinking about how SETI started, which is with this revelation that our current radio transmission technology in the late 50s was sufficiently bright to be detected by our radio reception technology at the same time at interstellar distances.
Yes.
Uh, and that was that Cocconi and Morrison paper in 1959 really kick-started the idea of modern radio SETI.
Hmm?
And I think something that's not as much appreciated is almost exactly the same time, 1961, you had this uh, kind of same revelation, but with the laser. So at optical wavelengths,
Hmm.
you have this kind of similar calculation done in part by Charles Townes, inventor of the laser,
Yep.
that you could do the same thing with optical communication. And that one was kind of more theoretical, but both papers sort of came to that same conclusion
Hmm.
that we were now at a point in human technology where we could send messages between stars.
Nice.
And
Patient.
the we kind of go from here and start thinking about all of the different impacts that humans have had on the Earth. So all the way from some debated signatures, even like 10,000 years ago,
Mm, okay.
uh, up into the present. And so that's, yeah, that next paragraph there.
Uh-huh. Uh-huh.
And a lot of these things, like human extinction of megafauna and these kind of signatures, are very like still debatable in the record. But I think it's undeniable that as humans spread over the Earth and develop technology, that you end up with a lot of impacts that are at least remotely detectable from Earth orbit, and then maybe from further beyond.
Mm. Yes. Cool.
So I think it's a good time to go to table one here.
Let's a
Um,
little bit.
the upshot of this section is that as we create telescopes or detectors to detect certain kinds of signals, the time that we create a transmitter for that type of signal tends to be relatively temporally linked. Now, there are a couple examples on here where we don't have, say, a gravitational wave transmitter yet, and that one
That
might be a
might be
bit
a
of a
little bit.
stretch. Um, but in general, the development of these technologies, more on the engineering and R&D side, transmission and detection go hand in hand. And uh, that kind of brings us to the main idea of the paper, which is that as we are looking out into the universe with telescopes at all of these different wavelengths, we also are emitting uh, technosignatures or signatures of our own technology that might be detectable in those wavelengths
Yes.
from the other side at interstellar or interplanetary distances.
Hmm?
Um, so if we use Earth in a mirror as a mirror in
Okay.
that way,
Okay.
uh, then we come to this idea of the ichnoscale. So this is Hector Socas Navarro's idea from a 2021 paper, which is that if we consider an ichnoscale value of 1, that is Earth's present technology.
Okay.
If we said, okay, let's say radio transmissions at an ichnoscale value of 2 could be interpreted as twice the sensitivity in a radio telescope or twice the brightness in a radio transmitter
Okay.
than the best thing we have today. So
Okay.
it's a normalizing factor to present day Earth technology.
Got it. Okay. Hmm. I like
Uh,
the word here, ichnoscale. I hadn't heard that one before.
it's a fun word.
Yeah.
And it's a helpful concept for this paper um, because in SETI work, there's a lot of extrapolation to future technologies.
Yes.
That is something that's been part of the field all the way back from Dyson spheres and Dyson structures very early in the field's founding.
Yes.
Imagining technologies that are hugely beyond anything that we can do right now and seeing if we could search for those with present day instruments.
Kardash, what do I got? Kardash scale? Kardash,
Uh,
something.
Kardashev,
Kardashev. Thank
Kardashev
you.
scale.
Yes. Yes. Hmm.
um, and that's all well and good, but it kind of bothered me that we spend a lot of our time looking for technologies that don't even necessarily have a proof of concept
Correct.
uh, in our own Earth history or Earth technology.
Hmm.
And so the idea of this paper was to say, we are setting our capabilities at ichnoscale of 1.
Hmm.
We're not imagining any far future telescopes. We're not imagining any far future technologies that could be detected at large distances. We're
Hmm.
stuck with only what we have today.
Right. Good.
How far away could an Earth detect an Earth?
Good. I love it. It's great. It's a very nice concept. Good.
Uh, so this is something I will say, I don't know if it's necessarily in this section, but this is something that comes up, like has come up in the SETI literature before, but generally only for radio. So there have been calculations of like how far could our best radio transmitters be detected by our best radio receivers,
Yes.
but SETI is a lot broader now. It's been broad the whole time, but it's getting broader as time goes on,
Hmm.
and
And deeper.
and deeper. And so this has never been done where we could actually compare Earth's detectability across the multi-wavelength array of technosignatures that we now produce.
Right.
Um, so that's what we wanted to do in this paper is to say, like, okay, there are all of these different methods that have been proposed with the assumption that we can't assume technosignatures far beyond what we can produce right now. Which of these is going to give us the most detectable signature?
Okay. I'm with you.
Uh, so the first part of this project was brainstorming what signatures are produced by modern day Earth that could be detectable. I think our line was from Earth's orbit or beyond, that you did not have to descend into the atmosphere to see.
Okay. Okay. Hmm.
Uh, and I think our spreadsheet had like a dozen rows or something, and we've condensed it into various sections in this paper.
Beautiful.
Um, but we went through radio transmissions, which are the
Mhm.
kind of classic one as our first example. Uh, and then we go into
Yep.
atmosphere and other things as the paper goes on.
Yes, yes, yes. Famous one there.
So yeah, let's start with the radio.
Yeah.
Um, there are so many different classes of transmitters on Earth now, so many different orders of magnitude of transmission power, and many different things that we use radio waves for.
Hmm.
So we kind of break this section out into different categories of radio technology.
Yeah.
Um, the top one here, the intermittent celestially targeted radio transmission, is uh, things that are either like intentional METI signals.
Yep.
So this is signals that mostly for uh, sort of as a proof of concept or a bit of a like art or philosophy project in a way.
There you go.
We sent high powered signals out with the Arecibo telescope, most famously,
Yes.
um, signals that were putatively intended as a message,
Mhm.
and so we're supposed to be as bright as possible.
Okay.
Um, and Arecibo's transmissions, not just for METI, but also for radar astronomy, are
Hmm.
the most powerful transmissions that humanity kind of can, or at least was previously able to, send out into the galaxy.
Pretty good.
So a 20 terawatt EIRP,
Yeah.
where EIRP always throws people. So this is the you take your sort of solid area on the sky that your beam would cover, and then say if that much power was visible from any point on the sky, so you have
Yes.
an omnidirectional antenna that is producing that much power at any vantage, how much power would that transmitter have to be?
Yes.
Uh, or have to have. And so that's where the 20 terawatts comes from. If you look up in a manual, Arecibo's transmitter power, it will not be 20
Not be 20
terawatts.
terawatts.
Probably
So
for the
it's
best.
basically the isotropic power.
Yes,
Yes.
equivalent isotropic power.
Very good.
Um, so that's sort of the gold standard here for any
Mm.
like calculating maximum transmission power. Of course, you'll note that we don't have Arecibo anymore.
I know.
So in this paper, we did make the choice to use whatever the high watermark was for the particular technology that humanity has reached, even if
Absolutely.
that is no longer attainable on the transmitter or detector side.
Right. Good.
Something that has been proved by existence at some point in humanity's history.
Hmm. Hmm.
And then there are drawbacks to those intermittent celestially targeted transmissions, mostly that first word there, the intermittent.
Yep.
Um, and so for fairness, we also considered like what are the largest transmitters that are on more of the time?
Okay.
And that's that second category,
Hmm.
persistent celestially targeted radio transmission. And for this, we used the Deep Space Network as our sort of example, because Deep Space Network, especially now, is just communicating as often as it can between all of our space assets and ground stations. And the so you get more persistent transmissions, still mostly concentrated in the ecliptic, which is kind of an interesting asterisk,
Hmm.
because that's where the stuff is that we want to communicate with in general.
Hmm. Yeah, the bulk of it.
Uh, and so that EIRP is considerably lower, but the transmitter is on much more of the time. And so we wanted to kind of consider that as a separate class of
Absolutely.
transmitter.
Hmm. Okay, I'm with you. Uh-huh.
And then the one that I always get asked about is category 3, which is persistent omnidirectional radio leakage.
Leakage.
So this isn't signals we're sending out into space intentionally, but the sort of collective signature of our cell phones, our televisions, our radio stations, our GPS, and everything else.
Mm-hmm.
Um, Now, I'll take GPS out of that one actually, because in this case, we're thinking about things that are located on the surface of the Earth and transmitting outwards.
Mm-hmm.
Uh, and here we're actually using Ramiro Saeed's estimate from his 2023 paper, looking at specifically 4G cell towers.
Okay.
Because the way these work, they mostly transmit sort of horizontally from their position to reach the ground around them. So not straight up, not straight down.
Right.
But that means that if they're on the limb of the planet, as seen from an observer, then they will be receiving a lot of that leakage power.
Mm-hmm. Okay.
Uh,
Cool.
there's still a lot of interesting work to do, I think, in characterizing the Earth's radio leakage, because that's one very particular kind of signature that has only recently been characterized.
Yeah. Okay. I'll ask that later. Okay. Uh-huh.
Um, but at least now we have an estimate as of a couple of years ago of what that power level might be, as
Mhm.
seen from a favorable vantage point. Because of course those transmitters are not kind of isotropically distributed on the surface of the Earth either.
Oh, yeah. That's actually a complex problem, isn't it? Yes.
We thought about solving it for this paper, and then I got into a 50 email chain deep thread and decided not to try it this time.
Another paper
Hmm.
follow up. Okay. And then there were four. Yeah. Where's our fourth one? Oh, here we go. Artifacts.
This one is somewhat for fun. So this is considering how powerful our radio transmitters are on the space assets that are being communicated with by the Deep Space Network.
Okay, cool.
So how strong are our radio signals that are being sent by things that are not actually on the surface of the Earth?
Mm.
So we're here using the strength of the transmitter on Voyager.
Yeah, okay. So 1.32 megawatt.
Yeah, so considerably smaller
Yeah.
than these other categories, but it's often used as sort of a an example or benchmark. And also, it's kind of interesting to think just like as that is our furthest artifact from Earth now, our
Yes.
signature that is furthest out there into the galaxy. It kind of is fun to see how that falls versus these other examples.
Absolutely. Absolutely. Very cool. Okay.
So, as far as the math goes here, we pick our transmitters, so that's what happened in the previous section.
Yep.
And then we want to figure out like at what distance we would be able to detect those transmitters based on some assumed receiver characteristics.
Okay.
And in order to do that, that's where these equations 1 and 2 come in.
Mm-hmm.
And I actually don't know that I want to go through this in too much depth,
Yeah.
but the basic idea is that the spectral flux density for a narrowband source, so how brightly you're going to see that source,
Yes.
is dependent on the signal to noise you can get. It's dependent on your channelization. So, what is your frequency or wavelength binning that you've chosen?
Right.
How sensitive is your system, which is contained in that SEFD term,
Yes.
and then how many polarizations you have and how long you integrate.
Ooh, polarizations. Yeah, yeah. Okay. Uh-huh.
And a little fun thing about how the transmitter's width compares to your receiver channels, which we make a nice little simplifying assumption in here.
Okay.
Um, so something I'll mention just because it was kind of a fun consideration in this paper is we had to pick integration times for almost all of these signatures, right? You have to
Ooh,
choose how long you're looking at something to know
right.
what distance you can detect it at.
Right. So what's the upper limit of that integration?
So what we did is we chose sort of field standards for each signature. And so here it's somewhere in this section. I feel like we used something like a 5 minute or an hour.
Yeah, T of
Yeah,
the
an hour.
integration time. Do. Yeah,
Um,
1 hour. Yeah.
now
Yep.
that's I actually thought that we might get a lot of questions about this when we publish the paper because I feel like everyone would look at their favorite signature and be like, "Well, why wouldn't you just integrate for 20 hours?"
Or 20
Um,
years, or 20 years, right?
exactly. So we tried to match it to kind of reasonable assumptions that are made for an interesting target in each of these different regimes.
Okay.
So generally we do 5-minute scans, maybe 10-minute in radio technosignature work. You could do an hour for a particularly interesting target, and so that's what we chose here.
Okay.
And then you start getting into interesting considerations like nonlinearity of a drifting signal and things that make that more complicated.
Right.
But it's still an arbitrary cutoff. So that's something I will put out there is things like the signal to noise, which we kept as 5 for
Yep.
every signature,
Okay.
and also the integration time. Our choices that we made, we tried to make reasonable ones, but there's no kind of right answer necessarily for these, especially comparing very different methodologies.
Right. Okay. But you take your best shot at it. Okay.
Exactly.
Here's 164. Okay. Hour. Okay. Cool. And then.
So then you kind of plug in your numbers into those equations up top
Yep.
and find for each of these different cases the detectable distance of that signature using the square kilometer array, SKA mid.
Yeah. Mm-hmm.
So we're cheating a little bit in some of our reception technologies. We're using SKA, and you'll see in the next section we're using habitable worlds, which is the furthest one out that we chose.
Uh-huh. Mm-hmm.
Um, but we decided that reception technologies that we were quite confident would get built, and that have already been sort of fully spec'd out, where it's like we could totally do this. It's just a matter of time and money. And this is something that, has been shown that institutions and agencies are interested in investing in. We did decide to go with those technologies, so these near future astronomical technologies.
Mm-hmm. Mm-hmm. Well,
Again, somewhat arbitrary. We could have done Arecibo, and we in fact ran our numbers for that as well, just as we were trying to make that decision.
mm-hmm.
Um, but yes, in this case, each of these transmission technologies from SKA, you get the following distances. And the most interesting number is the big one
Yes. 12.
that Arecibo to SKA mid can be detected at 12,000 light years.
Even
Um,
we haven't been transmitting it for 12,000 years.
absolutely.
They're still getting.
So,
Mm-hmm.
more of the fun things that we kind of we don't sweep under the rug necessarily, but are good caveats to put forth.
Okay.
Of course, you can't actually see it at 12,000 light years till we've been transmitting for 12,000 years, so we are neglecting travel time.
Yes.
And then we are also assuming that the signal will be self-evident. We are assuming no ambiguity,
Okay.
which makes sense in the case of narrowband signals like these examples.
Mm-hmm.
It should be pretty obvious that these are technologically generated because they are narrower than the thermal broadening you expect from natural processes.
Okay.
Once we get to things like the atmospheric technosignatures, I would not claim a detection at SNR5 without considering other uh, potential confounders and false positives.
Yes.
But for this paper, we are doing that.
Okay.
So we're just saying that you know exactly what you're looking for, just can you see it?
Good. I'm with you. Mm-hmm.
Um, all right. So for that next section there, I will skim over some of this work because I am not an atmospheres person. This is Ravi Koparapu's contribution to the paper.
Nice. Good shout.
Um, the general idea is that humans have, of course, rather famously been adding things to our Earth's atmosphere
Chemistry. Yes. Mm-hmm.
over the last several decades, and that is having planetary scale effects and forcing effects.
Yes.
And uh, we considered CO2 as the main example, which is, of course, the gas that is most prevalent when we talk about climate change and sort of think about it from a policy perspective. You think about CO2 or methane as greenhouse gases.
Yes.
But the astrobiology community has, of course, very early on recognized that these have a ton of abiotic sources and are not particularly good markers of technology.
Yes.
Um, and so mostly we avoided those in this case just because the more interesting modeling to be done is on things that are more definitively technological.
Like chlorophyll.
So chlorofluorocarbons, or CFCs, are created by human technology and have only very small natural fluxes from abiotic or non-technological sources.
Mhm.
Um, Nitrogen dioxide is a little more ambiguous. It has different combinations, but our technological flux of NO2 is kind of much a large and significant contribution now to the NO2 present in Earth's atmosphere.
Yeah.
Um, and so what we ended up doing is building on work from two previous papers that explored these gases, so NO2 and CFCs. And so those gases are our transmitter for this section.
Hmm.
And then our reception technology here, as I mentioned, is the habitable worlds style concept. Here we called it LUVEX because at the time the name had not been sort
Ah.
of decided on.
Okay.
um, and I think, yeah, if you scroll up there,
Yeah. Yeah. Yeah.
um, the
Right.
difficulty was just that the way the results were presented in some of these other papers was just a difference in like which parameters you focus on. So they bumped up the concentration in the atmosphere until it was detectable at inter or sorry, until it would be detectable from actual sources that we might observe with HWO.
Okay. I'm with you. Hmm.
Whereas in this paper, we're like, well, we don't care if there's an actual star at that distance. Just tell me what the detectable distance would be for Earth-like concentrations. You don't get to bump it up anymore.
Yes. Yes. Uh-huh. Uh-huh.
Um, so here we switch to focusing on NO2 because its spectral signature will be detectable by HWO just by wavelength range, whereas the CFCs, that's not the case. So it's just one of these will be in the observable wavelength regime and the other one will not.
Okay.
So we focus on the one that will. We look at the highest concentration of global NO2, which was in the past. It was in 1980.
Interesting.
This is a kind of nice optimistic point. We've actually managed to reduce our NO2 emissions since then.
Hmm.
Use SNR5 and adopt a very optimistic 300-hour observing time for a target that HWO would really, really like to observe.
Good luck with that tack.
Yeah, absolutely. So in you kind of put all of these into the 1D photochemical model, or at least scale the results of the photochemical model from Kaparopo et al.,
Hmm.
and find a detectability distance of 5.7 light years, um,
Cool.
which maybe I'll come back to this later as well, but is pretty good. Is much better than we could have done in the decades prior.
Yeah.
And it's not just I think a lot of people interpreted that as like, oh my gosh, we've polluted so much more that we're detectable further. But it's actually just that our astronomy has gotten so much better that we can detect things further.
That's the I=1 bit, right?
Yes. And so that's the interesting trade-off or balance there, is
Right.
it's how much has the signature grown, but also how much better has our reception technology gotten.
I guess it's not I. I guess it's iota. Right? It's iota.
Yes.
Okay. Okay. I'm with you. Cool.
All right. So on to our next signature here, optical and infrared emission. So here, honestly, this is Thomas Beattie's contribution. Very similar sort of setup to the atmospheric technosignature section. Thinking about looking for city lights on Earth's night side as a source of illumination that could be remotely detectable.
Yes. Yes.
So I believe we're still making the sodium light assumption, which is becoming worse and worse as we
Right.
change.
Right. Going away,
Um,
but currently still there, definitely.
mhm.
Hmm.
And then
Okay.
if you scroll down a bit,
Yep.
um, existing work on this topic had done sort of the same thing as the atmospheric section, where you say, okay, how many city lights do you have to put uh, on a planet in orbit around a nearby star for it to be detectable with HWO?
Okay.
Um, and so we wanted to turn that question around and be like, you don't get to add more city lights. How close do you have to be in
Yes.
order to see
Yes.
the amount that we already have?
Given the yes.
So in that last paragraph there, we plug in the numbers. So this is 0.05% of our surface is covered by strongly emitting urban centers that will have a lot of that sodium emission line. And then, again, assuming 300 hours of time on HWO, you need to be at 300ths of a light year for a detection of SNR5.
Yeah, not so far.
Right. Inner edge of the Oort cloud
Kind of stuff. Yeah.
in the neighborhood.
Mm-hmm. Okay.
And then the optical and infrared umbrella sort of covers a lot of different ideas.
Oh
So
yeah.
now we jump to lasers.
Boom, the original towns. Uh-huh.
Um, and originally we thought about adaptive optics systems, producing our laser guide stars in order to do our own astronomy. We would potentially, ironically, maybe be detectable in that way. Um, However, uh, not really since I had started thinking about this idea, the deep space optical communications laser array sort of the prototype was built, and it seemed like a more relevant technology to use
Yeah.
because we're moving towards optical downlinks instead of radio downlinks for our spacecraft because we can
Bandwidth.
get much better data rates.
Yep. Yep.
Um, So instead, it almost becomes sort of an analogy to the deep space network calculation, but in the optical. And this section, both Pinch and Fawn and Macy Houston led all of this work, so I will not walk you through these equations.
Good. All good. Good shot.
um,
Mm-hmm.
but again, assume SNR equals 5, and then do both resolved and unresolved cases. Because it's not clear uh, initially how those distances are going to work out. And
Ah, gotcha.
once you run the numbers, yeah, either anomalous spectral feature or resolved point
Yeah.
source of
Okay.
spectral line.
I'm with you now. Okay.
Um, so we first did the unresolved case, but the distance that we get is 150 AU. And at that point, you can just resolve the Earth separately
Yes.
and the laser source separately. And in that case, you can sort of back it out and say, like, how far would this still be resolvable as two different sources and detectable based on the flux?
Yes.
And then that brings you to 1.8 parsecs.
Uh-huh. Uh-huh. Okay, I'm with you. Okay. Decent. Quite decent.
Uh, so you could improve this. This is still the idea of using these downlinks is still very new, so it's not completely clear how this technology is going to evolve, and that could change this calculation in the not too far future.
Right.
Um, but that could be done with chronography or other techniques.
Yes.
But that seems like a good estimate for kind of the technology that has been demonstrated so far for laser downlinks.
Iota equal one. Mm-hmm.
All right, and then we have a bit of a change of pace for looking at heat islands.
Okay.
Um,
Okay.
Almost a similar idea in a way to city lights.
Yeah.
So the premise of this section is that when we build cities, we trap heat.
Mm-hmm.
And you can see this remotely. You can see it very easily from an Earth orbiting satellite. And so cities are several degrees hotter than their surrounding environment,
Right.
up to 8 degrees C in unfavorable weather conditions.
Ooh.
Um,
Ooh. Okay.
and so here we use sort of the most extreme published estimate of 10.5 degrees C of just like assume a city is so much hotter than its surrounding environment.
Okay.
Um, this is going to be a really challenging
Yeah.
detection
This is
because
gonna
this requires you to resolve the surface of a planet, which is
Yes.
just
Yes.
not really something that we can convincingly think about doing for a long time. Um, However, we're going to assume, we're making this distance scale. We don't care whether it's interstellar or interplanetary, whether you're in the solar system when you make the measurement.
Right.
Um, so we kind of say, okay, we can spatially resolve the disk of the planet. We can see a hot pixel from an urban environment. And then as you move further back with something like JWST's MIRI,
Okay.
that instrument is going to be able to see this sort of resolved image that gets smaller and smaller, and at what point does the flux from that pixel dilute out into the surrounding pixels such that you cannot make a SNR5 detection anymore?
Mm-hmm. Yes.
Um, so that's sort of that dilution effect is shown in equation 5 there. Uh, and we think about like where the black body peak flux is going to be for a city of this temperature versus its surrounding area and kind of calculate um, that delta. And in
Okay.
the end, uh, you can dilute 72 pixels essentially linearly. So a 72 by 72 square with a single hot pixel in it, you would still be able to make the detection, just barely, and that's a distance of about 30 AU.
Mm-hmm.
Um, we decided not to take into account atmospheric transmission issues, so that would probably shorten the
Oh,
distance a bit.
right. Sure. Mm-hmm.
Um,
Mm-hmm.
so your
Yeah, you're gonna
your
dilute
transmission of
even
that.
more. Yeah.
Hmm.
Okay. Interesting.
But we mentioned that as a caveat slash open for future work and move on.
Good, good. Okay. All right.
So then we're getting to things that are going to be a little bit harder to detect at these large distances.
Mhm.
Um, but one human impact that is detectable throughout our solar system is our interstellar and interplanetary probes.
Yep.
Interstellar here, of course, meaning Voyager. But we have plenty of space assets within the solar system
So,
that, uh, if you got close enough, you might see either that they're like impact on a planetary surface if they're an asset that's on the surface of a body, like
mhm.
a rover or lander.
Yes.
Um, or you might be able to detect these objects via radar. So
Okay.
send out a ping and
Mhm.
notice that you're getting some sort of shape or composition or other information that does not look at all like a natural object in the solar system.
Yep.
So we actually start with the radar section here, and that's where the appendix comes in. If anyone really wants to know like how that calculation is done, there's a series of radar reflectivity and transmission equations at the end of the paper.
8 of them, and they're really awesome. People check it out.
But I think those three factors that you've highlighted there are sort of the important things to know. So, how strong is your original transmission? How large and reflective is your target?
Mhm.
And then how sensitive is the receiver that picks that echo back up?
Mhm.
So here we assume Arecibo's transmitter, same as case one in the radio section, as our radar transmitter, which makes sense because that's what it was used for. Um, I had a really fun deep dive here trying to figure out the most radar reflective objects that humanity had ever produced.
Ooh, okay.
And it is the echo balloons, which
Wow.
were actually intended to be passive communication reflectors. So they were
Wow.
designed to be as radio reflective as possible.
Cool.
There's some awesome pictures of these echo balloons in a hangar, and you can just see the scale of a person compared to this 40-meter
Oh, yeah,
mylar
yeah.
balloon. Highly recommend looking that up.
Very interesting. Okay. I didn't know that. Nice.
But yes, we go into a bit of a digression about that because I think it's cool.
It's very
And
cool.
and then we kind of continue on with our calculation. It's like, okay, we assume Arecibo transmitting, off reflecting off of an echo balloon-like object, and then receiving
Yeah.
here, I think, with Arecibo as well. Let's see. Yes,
Yes,
we
it's
did Arecibo to Arecibo.
bistatic. Uh-huh. Yep. Yep.
So then we make a bunch of assumptions that are described in the appendix and find that our detectable distance here is about a tenth, 1.4, sorry, 0.14 AU for the monostatic scenario
Okay.
for an hour of integration time.
Hmm. Not bad for just reflecting.
The D to the fourth really gets you.
Yeah.
That's what we learned. We hoped this would be better given how big the echo balloons are and how powerful our radar is, but power 4 is rough.
That's tough. Okay.
And then the second subsection here is for objects on planetary surfaces. So this is what I was talking about with either lunar landers or Mars rovers. And the largest human-made object on a non-Earth surface is the Apollo landing module.
Yes.
And so those are
4 meters.
about 4 meters in scale. And
Mhm.
then we've got some 3 meter scale rovers on
Curiosity.
Mars.
Hmm.
And here we actually do mathematically the same calculation that's done in the heat islands section.
Yeah, yeah.
So we're assuming like there's some brightness, you have some background brightness of your pixels, and then you're comparing your imagery here using the Lunar Reconnaissance Orbiter camera. So the near angle camera has the spatial resolution that you would need. Um, and you can actually see the lunar landing modules in LRO data. This
Oh,
is
yeah.
this is a thing that we have done. And so in this paper, we just say, okay, if you keep pulling LRO further and further back from the moon,
Right.
at which point do you not
Not
detect it
see it.
anymore?
Yes. Hmm.
And so doing all of that, we end up with a detectable distance of about 8,600 kilometers with LRO NAC to the lunar landing module using that same pixel dilution
Yes.
formula from
Yeah,
before.
yeah. Hmm. I'm with you. Okay. All right.
And it comes back again. The same simplifying assumption of just looking for a bright or a dark pixel in a grid. In what I think is the final section, it'll be sort of silly if there's something after this. What I'm going to say, the final section, which is thinking about our Earth satellites. So now we have, of course, mega constellations of satellites around our planet.
Ah, gotcha. Okay.
Um, and in the SETI field, there's discussion of this thing called a Clark exobelt,
Ooh,
which is an idea that the more and more geostationary satellites, especially that you put up,
okay.
the more opaque that section of the orbit is going to become.
Okay.
And so maybe it would be remotely detectable as a ring-like structure, or if you go beyond just geostationary, maybe the cloud of structures that you get from
Well,
the cumulative effects of satellite
yeah,
shadows.
exactly.
Here we're talking about in transit, say, against the background star.
Yes. Okay.
Um,
Wow.
so
Okay.
it's something that's been calculated a little bit for extreme cases of like how many satellites can we pack before we lose orbital stability. um, Thankfully, we're not at that stage yet. um, and we actually opted here to just choose a single orbiting object. In this case, the International Space Station.
Okay.
So the object that has the largest area, which is mostly the solar array.
Mm-hmm.
Um,
Yep. Power. Mm-hmm.
so when it comes down to it, we use here the DKIS telescope
Mm-hmm.
as our detecting technology.
Yep.
And the question is like if you're behind the Earth looking at it in transit and the
Yes.
ISS is there causing a little shadow,
Yep.
how far away can you pull DKIST before that shadow sort of merges with
It's
the
like
Earth and you can't
transit
distinguish it?
photometry, right? It's like transit.
Hmm.
Mm-hmm.
Um, so this section was also led by Macy Houston as a shout out there.
Good.
And uh, we get a detectable distance of 1.3 AU
Not bad.
for a very short observation time.
Yeah.
I think the idea here was that you would have to stack images and sort of know the position spatially in order to do that, and so that's the really short time.
Mm-hmm.
Um, and also the Earth transiting a pixel, the amount of time that takes before you have to sort of follow the tracking
Yeah.
across
Yes.
the
Ingress,
surface of the sun.
egress. Yes. And across. Yes. Uh-huh. Mm-hmm.
Um, all right. So I gave you a bunch of distances, and I don't remember half of them, even though I'm first author on the paper, so it's much more helpful to see them all next to each other. And I think it's easiest to do that with figure one.
Let's take a look at figure
It's
one.
also in the table if you want specific numbers, but
Okay.
uh, here we took all those distances, summarized all that discussion into
Beautiful.
uh, this single figure that gives you some also kind of handy dandy reference distances here for various objects in the solar system
Hmm.
and out into the galaxy.
Very nice.
Uh, so one of the things to notice is that the light blue points are the four radio cases.
Ah, okay.
And
If the colors meant anything, yes, they do. Okay.
those are the only ones that mean anything, so
Okay. Okay.
we didn't highlight that. But if you're looking at this figure, you kind of notice that those four light blue points are the ones that are at the largest distances in general compared to the other points.
With we got radio case 3, radio case 2, DSN, and planetary radar. Okay, cool. Uh-huh.
Um, but in the middle of those, we sort of have two interesting newcomers in a way.
Hmm.
The resolved laser case and the atmospheric NO2.
Ooh,
And I think these are cool
pretty good.
because the laser case is only going to get better as we move towards using more optical communications in our spacecraft downlinks.
Huh?
So
Uh-huh.
that's an area of a lot of activity. And so is atmospheric biosignatures and technosignatures and corresponding missions like HWO.
Yeah. Yeah.
So I think these could, for our ichnoscale equals 1 case, like I think humanity is doing quite well in pushing those to the right side of the plot here.
Right.
Whereas the radio cases, SKA will be wonderful and will transform radio science, but they haven't changed too much in comparison in the last couple decades.
Yes. Fair enough.
Um, and then you see sort of the smattering of all these other things, which are basically everything that you see once you're actually in the solar system.
Mm-hmm.
Um,
Mm-hmm. Okay.
so yeah, I know we're looking at the time there, and I don't want to
Don't
take too
worry about
long.
it. Don't worry. All good. It's all good. It's
So
fascinating.
yeah,
It's a fascinating topic, so we can stay on it for a little bit. It's perfectly great.
I'll tell you,
I
this
love this figure.
paper
It's great.
from conception to publication took like 5 years because it was very hard to compile all of these different signatures across so many different domains of astronomical expertise.
Really?
Uh,
So that was. Oh, okay. So that's when you started the draft. It's not when you actually submitted it. I was going,
yes, yes, no,
I
no, no.
peer review process. Oh my gosh.
uh, no, it turns out it's very difficult to just hop from methodology I haven't learned to methodology I haven't learned to try to try to
Oh,
put this
right
together.
on in APJ paper. Okay. So we do have a couple of takeaways, and all those are in those. Very
Yes. So
good.
first one we talked about, radio is still the way that Earth is most detectable if you assume a fixed ichnoscale of 1. Uh, that is makes sense. That's why it was kind of theorized as a good idea in the first place.
Right.
Uh, Radio waves are low energy. They don't get blocked by gas and dust. They travel at the speed of light. All excellent for
Perfect.
interstellar communication.
Mm-hmm. The watering hole.
Indeed. So then, takeaway number 2 is that my formatting is sad. That's fine. Um, investment in atmospheric biosignature searches has really boosted that value for atmospheric technosignatures.
Yeah.
So that NO2 value, if we assumed, whatever a previous telescope would be before HWO, this wouldn't even be a competitor. And then suddenly there's been so much investment that this is totally a plausible thing to do, which is really exciting and a
Mm-hmm.
very active new branch of the SETI field.
Very cool. Very cool. Uh-huh. Good. Good. Okay.
So, third takeaway here is that the remotely detectable impacts span 12 orders of magnitude, and I mean you can keep going if you don't arbitrarily draw the line at Earth orbit, but there's just such a variety and constellation of different signatures that we've imprinted upon our planet in different ways.
Mm.
And I think that's an area that definitely requires further study to really understand how are we impacting the atmosphere, the planetary surface, the solar system, the orbital environment of our planet, and kind
Mhm.
of looking at all of these things
Mhm.
as a whole, which is really interesting. And then
That
the
one
last one,
cracks me up.
the
Oh.
last one sort of has two sides to it. Um, a lot of the technosignature literature does focus on ichnoscales way bigger than one.
Yes.
Uh, and it makes sense. And sometimes we think about detectors that are sort of these far future concepts that are much, much better than what we can do right now.
Right.
And so we sort of said, like, okay, we don't want to be alarmist about the impacts of technology on our planet. We want to see, okay, exactly what are they and exactly how detectable are they?
Mhm.
And even for radio, you get a lot of anxiety among the general public about, like, oh my gosh, we're so detectable in the radio. Like, what if
Here
someone
they
finds
come. Here they
us?
come.
Exactly. Uh, and also just like, oh my gosh, like we're changing our Earth's atmosphere so much, and it is somehow like irreversible, or that these changes have reached some sort of tipping point.
Mhm.
And so, at least in this paper's framework, we can comment on that a little bit, and we can say that, like, we have caused remotely detectable impacts and impacts that are detectable from interstellar distances. But also, we find that a lot of the both reception and technology and transmission
Huh?
technologies that
Uh-huh.
we use in this paper are actually from the past, like the NO2 value being from 1980.
Right.
So these things are changing and changeable on relatively short timescales,
Yeah.
even thinking about the timescale in an like astronomical flagship mission or something.
Right.
Um, so it's like, yes, we do have these strong impacts upon the planet, but ichnoscale equals one really does change quite rapidly, and we should probably be wary in the literature about just extrapolating and saying, like, well, if you had 10 times the CFCs in the atmosphere, which will happen in, and then give some year, that's probably not a safe assumption to be making, given how quickly these things change.
You could subscript those iotas according to epoch, like what you do for RE and DEC, right? Or using 1950 or 2011, right? Yeah. Hmm.
Yeah, it's by definition a bit of a moving target.
Yeah. Good. Very cool.
And yeah, I think I mentioned that one before as well, which
Mhm.
is just we have this constellation of various orders of magnitude, and the closer you get, the more confident you are that you're seeing a technological civilization, a
Yes.
planet with a technosphere across different wavelength regions, and
Mhm.
with kind of all of these independently verifiable methods.
Good. Good.
Um,
Right.
which most of that happens once you're actually in the solar system, so that might not be maybe a practical recommendation for a while yet. But it is sort of an interesting thought experiment when so much of biosignature work is thinking about false positives and ambiguity. And
Right.
it's like, well, if we can get a constellation of a couple different independent lines of evidence, then that really increases our confidence in a detection.
Yeah. It's like multi-wavelength astronomy, so to speak, really.
Hmm.
Yeah.
Absolutely. And so that's possible for technospheres as well,
Hmm.
and biospheres if you look at different sort of families of molecules or things that you expect to be related to each other in their fluxes.
Yes. Yes. Very,
Uh, all right.
very.
So I think we've talked about a lot of these different considerations, um, biosignature pairs and I equals one and or iota equals one.
Yeah.
Um, but I do want to highlight one little section here in the discussion, which was a contribution by Connor Martini, who
Okay.
actually is a PhD student in religion at Columbia University.
Wow. Okay.
Um, and he's had some really fascinating insights and perspectives. He joined our group briefly for a couple years while this paper was like in prep, and at the very end, I think it's section 7.5 there on the next page. Um, we
Steady.
have the SETI as a mirror section, and we were thinking about, like, if you observed this constellation of technosignatures, what does each one tell you about the species that produced it?
Okay.
What could you infer?
Okay.
Um, and so there was a very sort of straightforward example in Sullivan et al., 1978, which was sort of the first Earth detecting Earth kind of paper, um, which talked about, like, oh, if you detected a radio technosignature from an exoplanet, you
Oh.
would see a rotational modulation that would tell you the orbital period, or not orbital, rotational period of that planet.
Uh-huh.
Which I always thought was so funny because it's like, if you've detected a technological civilization, that's going to be the news of the day. But also measuring exoplanet rotations is exciting. um,
Probably not. But it is
uh,
interesting.
Well, it is one of those things that, like, especially for terrestrial planets, we don't have any way of getting that information now, so it feels kind of funny to use a radio transmitter to do so. But we do see that modulation from Earth's radio signature. We see that it has a period of 1 day with some additional variations based on the continental distribution and things.
Right.
So we did a little bit of that um, in in this kind of last section here.
Uh-huh.
Thinking about like our artificial lighting would say that probably we have some biological sensors that are receptive to sodium light wavelengths. um, Maybe our reliance on radio waves implies that we can't sense those biologically, because otherwise it would be very noisy. Or maybe it's they
Okay.
would say, oh, well, you're using radio waves probably because you can detect them and pick them up, and you are your own cell phone. I don't know. Um, And so I really liked having Connor's input on this section because I was like, oh, you would definitely be able to figure out that our atmosphere is transparent to radio waves. And he was like, well, would you? And sort of challenged a lot of these assumptions,
Great.
which I think is important to remember that we can't
Very
extrapolate too far from the data that we take.
correct. Good.
Um, the other example there that your mouse is over that's kind of fun is like if they had data over time on our atmosphere and
Okay.
saw that NO2 and CFCs are increasing in concentrations so quickly,
Yes.
maybe that would be like, oh no, they're ruining their atmosphere. That's sort of the interpretation that most people would have. But maybe it would be like, oh, they're doing that so quickly, it must be intentional. They're terraforming, like
Right.
um, intentional international coordinated terraforming. So the interpretations are not straightforward for a lot of these things, and we have a bit of fun with the imaginative aspect
Right,
in
because
this
iota
section.
equals one here does not necessarily mean iota equal one there, or vice versa,
Hmm.
right?
Exactly.
Okay. Okay. Mm-hmm. Mm-hmm. You may come to some wildly different conclusions based on that. Very cool.
So
Well,
I think that kind of brings us to the end here. The conclusion, we just reiterate those points, the takeaways from our results section. And at the very end, if you scroll down, you can see those radar equations.
there you go.
um, we acknowledge Michael Bush there in the acknowledgments because I would not have been able to get through all this radar math without him.
Good. Cool. Always good to do that. Very nice. Very
All
nice.
right, I think that's everything I have to say about it. Plenty, I'm sure.
Oh, it's great. Sophia, beautiful work. Beautiful work. My congratulations to you and your co-authors. Very lovely. Very nice. And in AJ, no less. So very nice. Um, we just went through a whole paper on how dangerous it is to extrapolate to the future. But I'm going to ask a little one anyway. So where do you think we go from here, given the published article? What are sort of the next steps, either in what you may be doing on the next paper, or as a community, where do we go? So just sort of, where do we go from here?
Yeah, I think one of the things that I'd love to see come out of this is more of a community, not my own to-do list, is a lot of these calculations we made with quite a lot of assumptions. Like for the I think heat islands calculation, we're like, oh, we're not going to think about atmospheric transmissibility in these wavelengths. Um, and so I think there are a lot of calculations there, or when it comes to Earth's leakage radio signature,
Hmm.
that really could use dedicated simulations and analyses that we didn't do in this work.
Okay.
Um, that would be helpful generally. It'd be interesting, and it would also kind of update the values in this paper.
Yes.
And then the other thing that I think would be very interesting is to come back and redo this in 5 years, maybe 10 years,
Yes.
and see how these values change. And I think we'll probably see sort of the same thing that I noticed in this paper, where maybe signatures that, weren't so detectable before, if we have certain advances or just priority shifts in agencies or other things, we might see the disordering change because it's based on both our detectability and also our receptive capabilities.
Yep.
Uh, so very excited to come back to this again, in several years and see how this holds up and how this changes.
Yeah, it'll be really awesome to see this develop over the next half decade. It'll be very cool. Very nice. I'm looking forward to it. So nice. Sophia, thank you so much for walking us through your very awesome AJ paper. And that will do, everyone. And I hope this made your astronomy techno day just a little bit better. And we will see you on the next one. Bye-bye.